Hello everyone and welcome to Math 1342, Introduction to Statistics. This is Amy Hohers, professor at Lone Star Kingwood, and this is the first set of lecture videos for the class. There will be a lecture video for each chapter, and we are starting with chapter 1, which is on the nature and probability of statistics. It's kind of an introduction chapter. We're going to learn some definitions, and there's really not any mathematics in chapter 1. We'll get into the mathematics part of statistics when we get to chapter 2. So, just real quickly, this first section, this is, on the slides they don't label it very clearly, but this would be section 1.1. You'll see here it says chapter 1, section 1, so section 1.1. This is our textbook. If you've purchased a hard copy, that's great, but you don't need to purchase a hard copy. Within our homework system, Alex, you have a full ebook of this textbook. So we're using the 9th edition of the Bluman textbook, a brief version, elementary statistics. Again, if you have the access to Alex, the homework system, that has the entire ebook in it. Our learning objectives for the first section are to demonstrate knowledge of the statistical terms and differentiate between the two branches of statistics. So let's get into it. So what is statistics? You'll be surprised maybe to notice that the definition of statistics that we use here, it says statistics is the science of conducting studies. Well, why in a class that's called Math 1342 are we saying that statistics is a science? Is it a math or is it a science? And the answer is it's both. Statistics is really kind of a collision between science and math. Because what statistics does is it conducts studies, which are then used by scientists and sociologists and business people, all kinds of areas. But it is kind of a mix between a science and a math. So our definition says that statistics is the science of conducting studies. And you'll notice this sounds a lot like the scientific method. It's not exactly the scientific method, but it kind of sounds like it a little bit. In statistics, we conduct studies, or conduct research, you might say, to collect and then organize and then summarize, so kind of put it together, and then analyze and then draw conclusions from data. So we collect data. Okay, so we collect data, we do a study to collect this data, and then we organize it, summarize it, analyze it, and draw conclusions. And in this section, we're going to talk about the different branches of statistics and what are data. So a variable in statistics is a characteristic or attribute that can assume different values. Now, you probably have heard of a variable if you are, or have taken rather, an algebra class. In algebra, a variable is like your x or your y or your n. And in algebra, these are letters that represent an unknown number. But the reason they're called variables is because they can change. They vary. And so you have the same word, the same term that's used in statistics, but in a different way. But they're similar in that they can take on different values. So in algebra, you have x, which could be, 5, it could be 2. So it takes on different values. Whereas in statistics, a variable is a characteristic or attribute. Now, what do we mean by a characteristic or attribute? We mean anything. Let me back this up just a little bit and get rid of this. So what we mean by different characteristic or attribute, we just mean things like, say you're studying people. A variable for people could be their height. It could be the color of their hair. It could be their major in college. It could be what city they live in. Okay, so variable is just a characteristic or an attribute. If you're not talking about people, let's say you're talking about plants. It might be how long it takes that plant to germinate. I think that's how you spell germinate. It could be how tall it gets. So kind of like with people, it could be the height. But you could, any subject that you're studying, you're going to be studying some type of characteristic or attribute of that, and that is called the variable in statistics. So the values that a variable can assume are called data. And then a collection of data is a data set, and each individual value is called a data value or a datum. So let's go off of color of hair to kind of represent these. So when we're talking about the different values that a variable can assume, now remember, the variable is hair color. Again, let me back this up. I want to write this a little different. Okay, so we're going to say the variable is hair color. Then the data are the different things that you could list as hair color. Now, the researcher would have to decide how they were going to define that. Are you going to look at what the person's hair looks like right now? So if they have it dyed, it could be, blue, it could be green or something like that. Or are you going to go off of just natural hair color? I'm going to stick to natural hair color just because it's easier. And so, for data, you could have that they are blonde. You could have that they have brown hair. You could say they have black hair, red hair, gray hair. Those are the common hair colors. So that's the data. The data is the values that a variable can assume. So the things that you could select for a person. So you look at a person, you say, I'm going to write down data for that. I'm going to write down the information for that person, and you select from these 5 data options. And then a collection of data is a data set. So that would be after you have done your study, or as you're doing your study. The set would actually probably be considered when you're done. So let's say you had 5 people. Okay, so you had person 1, person 2, person 3, person 4, person 5. Person 1 had brown hair. Person 2 had black hair. Person 3 had brown hair again. Person 4 had red hair. And then person 5 had blonde. Okay, you didn't come across anybody that had gray hair. But you have 2 people that had brown hair, 1 person that had black hair, 1 with red, 1 with blonde. This is your data set. Your data set is brown, black, brown, red, blonde. That's the entire set of the 5 people that you surveyed. Of course, most studies would probably have more than 5 people, but it would be the entire collection of everything that you got from the people that you surveyed or that you researched. Each individual value is called a data value. So the first data value is person 1 is brown. So that's an individual data value. Now, I'm not going to give you anything like on a test or anything where I'm going to say, define a data value. This is more for when you're reading things, when you're reading problems, that you understand the terminology so that you understand what the question is about. So that's just the general terms here for variables and data. A variable whose values are determined by chance are called random variables. So what is a random variable? Well, a random variable is when you don't, when something can take on a value, any of the values that are data values, and it occurs randomly. So that would be things like rolling a die. This gives the example of rolling a die. So when you roll that die, it's just a random chance whether you're going to get 1, 2, 3, 4, 5, or 6 on a regular 6-sided die. If you draw a card out of a deck, it's a random. If it's shuffled up, it's random whether it's going to be a heart or a diamond or a club or a spade, or whether it's going to be an ace or a 2 or a king or a queen or whatnot. When you draw a number out of a hat, or a name out of a hat, like say you put everybody's name in a hat and you drew somebody's name out, that would be random. So when every data value or every data is possible, and selecting it is completely by chance, then that's random. So that's a random variable. Now this isn't random really because you're more likely to get some than the others. For instance, brown hair and black hair are more common than across the world than blonde hair or red hair. So those aren't exactly random variables. Random variables, again, are where each item in the data are equally likely to happen. I wanted to mention too, as I was setting up the next set of slides, I happened to realize I hadn't mentioned that you have notes in D2L that you can copy off that have these slides with some parts missing. So parts of the sentences, maybe some keywords might be missing from the slide. And if you print those off, you can use those to take notes while you're watching the video. Or you could put them on your tablet and take your notes digitally. But it'll allow you to kind of follow along and fill in some things without having to write everything down on the slides. And then also it will have, like, if we do a problem, it'll have the problem set up, but it won't have the solution. So you can write out the problem solution for practice as we're doing it. Okay. And you can find that in D2L. It says something along the lines of lecture notes or PowerPoint. I think it says PowerPoint notes. Okay, so our next definition or our next term is populations. So populations are very important in statistics because what we're typically trying to find out is something about a population. So let's say the population, or you have a population and it consists of all the subjects that are being studied. So all the subjects being studied. So it's what you would like to know about. So say that you want to know something about all the students at Lone Star College. That would be all the students across the entire system. So all at different campuses, different centers, and different certificate programs, degree programs, and so on. That would be your population. Okay, so the population is typically fairly large. And the problem with a population being very large is that sometimes it's hard to get information from every single subject within the population. When you can do that, when data is collected from every subject in the population, then that's called a census. So if you were able to, again, let's say we say the population is students, all students at LSC. Then if you could ask or find out information from every single student in the entire system, that would be called a census. The United States actually conducts a census every 10 years because it's mandated by the Constitution. But it's a very time-consuming and expensive process. And with most populations, it's either very difficult or impossible to get information from every subject within the population. So say it's something that's not, in records that you can pull up on, that somebody can pull up on the computer. Let's say you just want to, ask students, like, what's your plans after graduation? It'd be impossible to ask every student within the system what that is. And so in order to study a population, what happens most of the time is instead of taking a census and asking every single subject, we take a sample. Now, a sample has to be from within the population. For instance, if we're trying to find out something about the students at LSC, I can't sample students that don't go to LSC. I can't sample students that go to a different community college or who don't go to college at all. That wouldn't be studying the population. So your sample, this is supposed to be like a Venn diagram. So you have your population, and then within your population, you're going to take a sample. So this would be some students at LSC. And you hope that you can find a representative sample from within the population. So a sample is just a group of subjects selected from the population. It's not going to be the entire population. Again, that would be a census, but it's going to be a sample, a group from within that. If the subjects in the sample are selected properly, we hope then that they would represent the population as a whole. So we would hope that if we could say, let's go back to hair color. Let's say if we could randomly select, and we'll make our population, let's make it a little bit smaller. Let's say your population is this time let's say it is, your population is students and teachers and staff at a high school. Okay, so that's your population. Your population is the students and teachers and staff at a high school. And you want to know what their hair color is. So what you do is, instead of asking every single student, teacher, and staff at the high school, if it's a large high school, some of the high schools in this area have, 4,000 or more students in them. So let's say you take a sample of 200 students or 200 people at that high school. Again, you have to take people that are within that high school, otherwise you're not studying the population. So let's say your population is the people at this one high school, and so you sample 200 people. Well, we would like to select those 200 people randomly. That would be the best way. And then if we found out, say that, I don't know, let's say we find out that out of those 200 people, let's say 20, this might be a little high, but let's say 20 of the 200 people, actually let's make that smaller. Let's say you find out that 10 of the 200 people had red hair. Well, if you determine that 10 out of the 200 people had red hair, that's 5% of the population. Because 10 divided by 200 would be, whoops, I wrote 100 instead of 10. Just a second. Okay, so 10 out of 200, if you divide that, you get 0.05, which would be 5%. And so you could say, well, because in my sample, 5% of people had red hair, and I pulled that sample randomly, I'm going to assume that around 5% of the entire high school has red hair. And so let's say that the high school has, with the teachers and the students and the faculty and everyone, let's say that there's 3,000 students at the school, or 3,000 people at the school. Then you would say, okay, well, 3,000 times 5%, that would be 150 people. And so don't worry too much about the math for right now, but what we're saying is we use the sample to then use that as a prediction for how many people we think the entire population has. So the sample is used to determine information about the entire population, even though you aren't sampling the entire population. Okay, so the first type of statistics, if you remember in the learning objectives, one of the things was to learn the two types of statistics. Well, one of the types of statistics is what we call descriptive statistics. Now, descriptive statistics basically takes the definition of statistics, the process that we do when we're collecting statistics, and it kind of stops short. So descriptive statistics consist of just collecting, organizing, summarizing, and presenting data. And then it stops. So it doesn't make any predictions about it. It doesn't make any types of conclusions or anything like that. It just takes the data and then it can summarize it and organize it and present it, but then it stops at that point. And it lets whoever they're giving that information to make decisions of their own or make any kind of conclusions or relationships or anything like that on their own. So descriptive statistics, back to that slide that we had, the steps were to collect, organize, summarize, analyze, and draw conclusions. Okay, so in descriptive statistics, we do not analyze and we do not draw conclusions. Okay, so we stop short and don't do those two things. We just stop at the summarization and present that data as is. And so a couple examples of that would be the census. So the data is collected and then it's just presented. Now that doesn't mean that later people can't analyze it, but the researchers don't analyze it. The researchers just collect it and present it. They organize it, summarize it, present it. You might present it in tables, you might do charts and graphs, but that's it. That's where it stops. And one of the things that I want to kind of encourage you is when you're trying to remember these things, think about what the words mean. So in descriptive statistics, the reason it's called descriptive statistics is because all we're doing, the base word of descriptive, is we're just describing it. Okay, we're not going any further than that. We're just describing it. We're just saying, here it is, this is what it is. Just describing it, being descriptive. So the other type of statistics, remember we already had descriptive statistics. And the other type of statistics is inferential statistics. So when they say what are the two types of statistics, the statistics are either descriptive or inferential. Those are the two types, okay? So descriptive or inferential statistics. Now what's inferential statistics? Again, think about what the word or the base word for inferential is. Okay, so the base word for inferential is infer. And if you infer something in everyday language, we think of infer as kind of suggesting something. So an example in everyday language of inferring something is you might pull up in front of your home, you see your sibling's friend's car outside, and so in your mind you infer that the friend is at your house or at your apartment. Okay, so your friend of your sibling is over because you infer from the car outside. Okay, so you infer that the friend of a sibling is over because you infer from the car being outside that they must be at your house. Now, is that always correct? No, it's not. Maybe the friend is not over. Maybe their car broke down at your house. Maybe they did come over, but the sibling and the friend left and went to a movie. They does not necessarily mean your inference is always correct, and that's the same thing with statistics. Inferential statistics, you're trying to generalize from the sample to the population. So again, when we said, well, we think 5% of the entire population has red hair in this high school because 5% of the sample had red hair. And so we think there's like 150 people in the school. Now, that does not necessarily mean that's exactly correct. It may not even, it may be off enough that it's not really even close to correct. But if the sample is taken well, the inferences should be, typically be correct or close to correct. And so when you make that leap, when I said, I think this is what's happening with the population from the sample, that was an inference. I was doing inferential statistics when I said, I think 5% of the population. I didn't just stop at saying, this many, 10 out of the 200 students in the sample had red hair. I didn't just stop there. If I had just stopped there and just reported that, that would have been descriptive statistics. But when I went and said that I think that would mean that 150 people in the entire high school have red hair, that was an inference. Then I was going to the level of inferential statistics. And so let me write that down. So descriptive was, in our example, was when I said 10 of the 200 had red hair. Inferential is when I said, so about 150 of the 3,000, and it wasn't students, it was everybody, but 150 of the 3,000 people in the school have red hair. That's an inference. I don't know that for certain, but I'm assuming it from the information that I have from the sample. Okay, so descriptive is when I just stop with the information that I know for certain from the sample, and inferential is when you're making that leap. I always call it kind of a leap of faith or a leap of knowledge, or based on the information you have, you make that leap to inferential. And that's when you're generalizing from the sample to the population. You're going to be have estimations, so this is an estimation. You're going to do hypothesis tests, which we actually aren't going to do any hypothesis tests until chapter 8, I think it is. Yeah, it's chapter 8. So that'll be a while down the road, but we will do hypothesis tests, trying to determine relationships, like what does this cause that, making predictions. Those are all inferential statistics. So here's the example they say is, after taking a sample, descriptive statistics is done to summarize and present it. I guess it's not an actual example. But however, the goal of taking a sample is to draw conclusions about the population. And so in order to effectively make these inferences, we must understand probability, which is the chance of an event occurring. So let's say we know we're testing light bulbs for defects, and we get 3 out of 10 light bulbs are defective. If light bulbs aren't generally defective, then we know, well, that's kind of unusual. So knowing probability helps us with inferential statistics. And that's why for chapter 4 and chapter 5, we delve into the other mathematical topic of probability. So even though this class is called statistics, Introduction to Statistics, almost invariably in any statistics class, you will also have some probability, and we will do that for a couple chapters. Really heavy in chapter 4, and then a little bit more in chapter 5. Okay, so moving on. Just a really quick discussion about hypothesis testing, but again, we really don't do hypotheses testing until chapter 8, and so we do chapters 1 through 10, so it's almost at the end of the class. It's like pretty much our last thing that we do. And it's a process of evaluating claims about a population. So when we tested the light bulbs, we might assume 1% of all light bulbs are defective, and then we got 30% of the light bulbs in our sample were defective. So hypothesis testing gives us a way to determine if we can conclude that the manufacturing process needs adjusting based on this information. So if we only want 1% of the light bulbs to be defective at most, and we take a sample and we find out 30% of the light bulbs are defective, then that tells us a lot about whether our 1% goal is being met. And it can also be used to find relationships. So it says, for example, if you know the heights of parents, sometimes you can infer from past statistics what you expect, how tall you expect their children to be. So taller parents, taller children, shorter parents, shorter children. And so you have relationships. You can also have relationships like with medication. We believe if we give a patient this many milligrams of a blood pressure medicine, it will decrease their blood pressure by this amount. So that relationship is like a cause and effect relationship. But again, we'll come back to hypothesis testing towards the end of the class. And then the last thing we're going to cover in this first section of chapter 1, and this is the longest, one of the longer sections in chapter 1, is just this example on deciding whether something is descriptive or inferential. But we're also going to talk about this term placebo. So in the example, it says a pharmaceutical company wants to test a new drug that prevents heart attacks. They, in cooperation with a local hospital, find 300 people with heart disease, give half of them a new drug, and give the other half a placebo. So a placebo is a substance with no medical benefit or harm. So let's say these people are taking medication, but they're trying to give like a supplemental medication to see if it helps more. And so they give 150 of those people this new supplemental medication, and the other half, they just let them stay on the program that they're on and give them some sort of tablet that doesn't have anything in it. It might be a sugar tablet. Might have cornstarch in it. I don't know. Just different, think something that's not a medication. But it looks like the medication that the other people are getting. So the people who are taking it don't know it's a placebo. They don't know that it's a substance with no medical benefit. And then it says 50 of the people who received the new drug had a heart attack in 6 months versus 90 people who received the placebo. Gosh, that's a lot. They're really being dramatic with their numbers here. But so 50 of the people that received the new drug had a heart attack, and 90% that took the placebo had a heart attack. So you could say the new drug prevented almost 50% of heart attacks in the sample. That would be a descriptive statistic. They're not saying why, they're just saying this is what happened. The rate of heart attacks among people who got the new drug was 5/9 as much as the rate among people who did it. But if you wanted to go to inferential, that's when you would say the new drug reduces the risk of heart attacks by 50%. So this one, it's just saying what happened. It's just describing what happened. And this is saying what the drug did. So what the drug can do for patients. And this is descriptive. Descriptive is just when you kind of state the facts. You can summarize it. You could say it prevented 50% of heart attacks. And this is actually, they probably would say something like the patients who took the new drug had 50% less heart attacks. That would be even more descriptive. This is almost verging on inferential. But if they just said the patients in the study who took the new drug had 50% of the heart attacks of the people who didn't take the drug. But when you say, I think this drug reduces heart attacks, you're definitely going into the inferential. You're making an inference, you're making a generalization, you're making a prediction. So that's when we're getting into inferential. And so this would be inferential. Okay, so now moving on to section 1.2. And in this section, we are going to be talking about variables and types of data. We have talked about variables a little bit, but we're going to go into them a little bit more. And the learning objectives are to identify types of data and to identify measurement level for different types of variables, for each type of variable. So our first terms that we're going to learn are the terms qualitative and quantitative. I cannot emphasize enough when you're trying to remember these, try not to just memorize them. Try to remember them by what the word means, because these two words are very similar to each other, qualitative, quantitative. They both start with QEA, they both end with TIVE, they're very similar to each other. So don't remember these by memorizing. Think of what the base word is. So with qualitative variables, the base word for that, of course, is quality. So when you think of something, if you say, name a quality of that person, you're going to probably say something like they have, again, going back to hair color, they have black hair, they have brown eyes, they go to Lone Star College. You're going to name some sort of category about them. And so a qualitative variable is a variable that has distinct categories. Sometimes these are, instead of qualitative, they're called categorical variables. Those are pretty much interchangeable. Our book typically uses qualitative, but if you hear categorical, it means the same thing. So qualitative variables are generally non-numeric. Now there are a few things that are numerical that are still qualitative, but in general they're non-numeric values. So you might say the examples they give here are birth month, hometown, favorite color, school that you go to, what grade you're in, what classes you take. Those are all qualities of a person that don't necessarily have a numeric value to assign to them. Now, on the other hand, when you talk about a quantitative variable, the base word of quantitative is, of course, quantity, which means amount. So when you're talking about a quantitative variable, you're talking about amount, which is typically a number. Okay, so up here, a qualitative variable is a characteristic, whereas a quantitative variable is a number. It's still describing something about the subject, but it's typically some number value. So for instance, quantitative variables for a person might be their age, their height, their weight, their shoe size, things like that. Things that are numbers that describe the person. How many credit hours you've earned. That would also be quantitative. And the thing about quantitative values is because they're numerical, you can sort them from smallest to largest. So you could say someone who has earned 10 credit hours has earned less credit hours than someone who has earned 20 credit hours. Because 10 in that situation, the number 10 means they have less credit hours. Okay, so now let's go on to a subset, or the two subsets of quantitative. So qualitative data variables are just qualitative variables. But quantitative variables can be further broken down into two categories. So quantitative variables can be listed as either discrete or continuous. Discrete meaning very focused. This one's a little bit harder to tie back to what discrete means, but discrete means kind of focused. And in this case, discrete means it has to have a countable value, like 1, 2, 3. It actually can technically have negative numbers, but it doesn't often. So you can kind of think of it as it needs to be counting numbers. Or at least integers. One thing I could think of that would be considered discrete but is not a counting number is like your account balance or something like that in dollars to the nearest dollar. You could say, well, I am overdrawn at the bank by -5. So that would be still considered discrete if you were listing it to like the nearest dollar. But most of the time with discrete variables, mostly it's 1, 2, 3, etc. And then a continuous variable is anything that has an interval. Now, continuous, if you were to think of like a number line, think up here of a number line. So if you think here of, 0, 1, 2, 3, 4, discrete variables would fall right on one of those spots if you were to like put a graph. Now, when you're talking about continuous variables, we still might be in the same span of numbers, but continuous variables don't have to stop on the whole numbers. They could be anything in between. So they could be any of these numbers on here. So you could have 0.5, 0.8, 1.2. Now that doesn't mean that it can go out to any number of decimals. It doesn't mean you can have numbers like, pi that doesn't ever repeat or something like that. But you can have values in between the values. So typically what we'll say with this is that continuous variables are numbers where you can have fractions or decimals. So height is typically a continuous variable because you could say someone is say 62 and 1/2 inches. You don't have to stop at the nearest inch on somebody's height. Again, though, somebody could define it where they're going to say, I'm going to round it to the nearest inch, and then you've made it a discrete variable. But if you're going to allow decimals or fractions, that becomes a continuous variable. So the book just provides here kind of a nice little flow chart for determining data. So it shows, data can be broken down into either qualitative or quantitative. If it's qualitative, that's kind of the end of it. That's a category, and then we stop. If it's quantitative, numerical, and can be ranked, then that can further be broken down into either discrete or continuous. So if somebody says it's a continuous variable, you automatically know that it's quantitative because continuous variables are a breakdown from quantitative. So if you're a visual person, that might help you remember that a little bit better. So we have 4 examples here. So we're going to go through, each of these, are they discrete or continuous? So the hours of YouTube watched per day. Again, you could define that and say we're going to round it to the nearest hour, but probably not. So this is going to be generally thought of as continuous. And that's because it doesn't have to stop at 1 hour, 2 hours, 3 hours. You could have 1.7 hours as your answer. And so once we start going into this realm of having decimals or fractions in our answer, then we call that, in statistics, we call that continuous. Number of books read in a year. Now, again, that could be up for discussion because you could say I'm partway through a book, so I've read, 22 and a third books. But if we're going to say maybe instead of number of books read, maybe number of books completed in a year. So if you're just talking about the ones you've completed, then that would be discrete because you've either read 0 or 1 or 2 or 3, etc. It's just going to be a counting number. So the number of books you've completed in a year would be typically considered discrete. Number of apples on the tree, can that be a fraction? Can you say you have, 23 and a half apples? No, probably not. You would count the apples and you would list it. I have, again, there's 25 apples on the tree. There's 30 apples on the tree, but you're not going to have a part of an apple. So again, this would be discrete. And then weight. Pretty much anything that can be measured with, some sort of an implement, like a measuring stick, a thermometer, those types of things, those tend to be continuous because, again, you can measure in between. And so the weight of delivery truck could be, if you're measuring in pounds, it could be, 2,574.8 pounds would be reasonable. But again, somebody could define this as being discrete by just saying we're going to round it to the nearest pound and only allowing the whole numbers. Then you could call it discrete. But if you're not doing that, if you're allowing partial weight, then you would call that continuous. And then here's the book's descriptions of these. So it says hours of YouTube watched, hours is measured, and the possible values could be fractional, 4.3 hours, for example. Number of books is discrete because it's counted. Number of apples is discrete because it's counted. And then weight of a delivery truck is continuous because it's measured. So again, they're kind of differentiating between being measured, being continuous. So measured is typically continuous, and then counted is discrete. So if it's counted, they're calling that discrete most of the time, and then if it can be measured, it's continuous. Continuous because it's measured, discrete because it's counted. And you'll have practice of this in your homework. You might miss, even if you basically understand it, you might miss a couple on your homework the first time through, but you get multiple attempts on your homework. So hopefully by the time you do a few, you'll be solid on the understanding of it. Okay, so now we're going to get into the one part of chapter 1 that is a little bit mathematical. And we're going to talk about class boundaries, continuous variables and class boundaries. So because continuous variables are measured, and then at that point that it's measured, it has to be rounded. You have to decide whether to round to the nearest pound or whether to round to the nearest tenth of a pound, to the nearest eighth of an inch, if you're measuring a distance or a length. And so because of that, we have to have a decision point. We have to decide where are we going to start calling, when we're measuring something, when are we going to stop calling it 10 inches, and when are we going to start calling it 11 inches? When are we going to stop calling it 10.5 and start calling it 10.6 inches? So there has to be a boundary that makes that as the point of decision between the two numbers. So for instance, it says the boundary of 112.3 pounds is 112.25 excuse me, to 112.35, because any weight greater than 112.25 would be rounded to 112.3, and less than 112.35 would get recorded also as 112.3. I find this description students just don't really grab that by reading that paragraph. So let me try to draw you a visual. So we've got the measurement, the value that's going to be recorded. If you were going to record 112.3, what could have been measured that would have been written down as 112.3? Well, if you're rounding to the nearest tenth, because this is rounded to the nearest tenth, that means that before 112.3 there was 112.2, and after it would be 112.4. So at what point after 112.2 would you start rounding up to 112.3? Well, it wouldn't be at 112.22 or 112.23. It would be when you get to the middle. So when you get to the middle right here is when you would say, okay, I'm now closer or as close to 112.3 as I am to 112.2. And typical convention is when you get to that halfway point, when you get to a 0.5, you round up to the next. And so this would be 112.25. It would be halfway between 112.2 and 112.3. Some people like to think of it, if you think of this as a 20 and a 30, that might be a little easier to understand. 20, 25, 30. I'm going to take that off because it helps some people and it confuses other people. So I'm going to put it there, and if you like that, you can write it down in your notes, but I'm going to take it off for the moment. Okay, so 112.25 is when you would start rounding up, and writing down in your, your data that that's 112.3. And then if you go on the other side, the question is, when would you stop calling a value 112.3? Well, it would be when you get halfway, because when you get halfway, you would start calling it 112.4. And so halfway between 112.3 and 112.4 would be 112.35. And you might say, well, but why is that listed when that actually gets rounded up to 112.4? Well, if you remember from algebra, when we graphed, when you use it could be either a solid dot or this square bracket. This is the included point. So this point is included and gets rounded up to 112.3. This point is not included, but it's still the boundary. It's the point that it changes. If you were graphing this with the open circle, closed circle, this would be an open circle. Okay, so you could think of it like that. So anything that is at 112.25, you would record that as 112.3, all the way up until you get to 112.35, then you would stop. Okay, so those are considered the boundary values. They're like the changing points for the decision. At what point do we stop calling it 112.3? Okay, and you'll notice that these go out one more decimal point, and it adds on a 5 typically. So let's look at some other examples. So let's say we have 73 degrees Fahrenheit. So again, think of, I always tell students, if you have any problems with this, draw this little picture out. So you've got 73 here, right? What would be below 73? Well, the next recorded value below 73 would be 72, and the value above it would be 74, because this indicates that we're rounding to the nearest whole number. Okay, so we're rounding to the whole number. So what would be rounded to 73? Below that would be 72, above would be 74, but what value would you get for a temperature that you would call in your recording 73? Well, it would be halfway between 72 and 73. So 72.5. And then 73 to 74, you would stop calling it 73 when you got to 73.5. So this is where you start calling it 73. This is where you stop calling it 73. So this value would actually be included as 73, and this would be not included. As soon as you get to that point, you're going to then start rounding it up to 74. But anything in between here is going to be recorded as 73 degrees. So if you got a measurement of 72.5 or 72.7, you're going to say 73 degrees. It's the closest, that's the closest one. But then when you get 73.5 or anything bigger, then you're going to start rounding it up to 74. So on this one, this is more similar to the first one we had because it's rounded to the nearest tenth. Now, if you want to practice, just pause the video for a second, okay? And see if you can create this number line for yourself for this problem. So the length of the frog is recorded as 17.9. We'll start with that. And then if you want to try to do it yourself and see if you got it correct, just pause the video and write down in your notes what you think it is. That's what I would have students do in class. And then come back. Okay, so 17.9 is the value that we're rounding to. What's below that? 17.8. What's above that? 18. Actually, it's 18. 18.0. So the middle, where we would start rounding up to 17.9, would be 17.85. And where we would stop rounding to 17.9 is when we got to 17.95, then we would start rounding up to 18. So the boundary values are 17.85 to 17.95 for 17.9. Okay, so here 72.5 and 273.5. Here it would be 17.85 to 17.95. Now this one is a little confusing because it's time. So this is probably 13 minutes, 1 second, and 1/10 of a second. Time can be written different ways, sometimes with different sports, but probably 13 minutes, 1 second, and 1/6 of a second. So we have 1301.6. What would be below that? You would have 1301.7, and up below that you would have 1301.5. So when would it be rounded up and when would it be rounded down? Well, the middle here would be 1301.55. Halfway between 0.5 and 0.6 would be 0.55. Remember, if you like it better, you could add on that extra digit here. So you can see 50, 55, 60. Okay, and then over here, you would have 1301 point, we want halfway between 0.6 and 0.7, that would be 0.65. Because 0.7 would be like 0.70. So 60, 65, 70. So the values here would be, the boundary values would be 1301. Sorry, it's hard to write 3s with this digital pen that I'm using. To 13.01.65. 1301.65. And then this is just their explanations of it from the slide. Same values that we got. Now, another way that we can classify a variable is by what we call a measurement scale. There are 4 levels of measurement that we can use. We can use a nominal level of measurement, ordinal, interval, and ratio. Now, it says here qualitative variables can have the nominal level or the ordinal level. That I will agree with. But it does say here that quantitative variables can have the interval or the ratio. There is a little bit of overlap here. Quantitative variables can only go to ordinal. This isn't a hard and fast rule. It's just kind of a general. Okay, so I'm just going to put that over here. Okay, so we have the 4 types. We have nominal, ordinal, interval, ratio. And I always tell students this is one that you might just want to kind of try to come up with a acronym for it, NOR or something like that, to help you remember the order of them. I'm gonna give the definitions of them, and then I'm going to show you a visual for this, a couple visuals for this that will help you see it a little bit better. But we'll go to the formal part first. For nominal and ordinal, nominal level of measurement is data that puts it into mutually exclusive, which means they don't overlap categories, but there's no natural order or ranking. So basically all you can give the variable or the data is a name. So you can see how that could be, that's just a qualitative data. It's just a quality. So how do you remember that? Well, you may not know this because it's not quite as obvious, but the base word for nominal is actually name or noun. And so nominal is a name. So if you can only name it, then that variable only reaches to the nominal level. Now, when you go to the next level, it still meets the criteria for the prior level, but it also meets these criteria. So everything, basically every type of data, you can give a name to. So every type of data is nominal. Now, if data can reach the next criteria, then we say that it's nominal and ordinal. So ordinal level, of course, the base word of ordinal is order. So if it can be ranked or ordered, whoops, that didn't go very well. Hold on a second. If it can be ranked or put in order, okay, so if you can put it in order, it's ordinal. So in this case, though, it doesn't have to be numbers. So for instance, when a person gets first, second, or third place in a race, that's the order that they came in. The first person, the second person, the third person. One that's even maybe a little bit less or more obvious that it's not a quantitative value would be like small, medium, large. So small is smaller than a medium, is smaller than a large. You can put those in order. If three people, different people got different size drinks, you could put them in order from, smallest to largest, but that's not really a number. So you can put it in order. If it can be ordered, then it reaches the level of ordinal. Again, numbers reach that level, but it's not the highest level that they can reach. So we typically name the highest level that a variable or a piece of data can reach. Now, the next thing that we're going to talk about are the interval and ratio. So with the interval, that's typically when we get to units of measure. So we have consistent intervals. So if you go back to, say, a small, medium, and large drink, those aren't necessarily consistent intervals. From a small to a medium, you might add 15 ounces. And from a medium to a large, you might add 30 ounces. So let's say this is 10 ounces, this is 25 ounces, and then this is 55 ounces. Those aren't consistent. Here you went up 15, here you went up 30. So they don't have consistent intervals. But when you're measuring somebody's height, and you go from, somebody is 5'6" to somebody who's 5'7" to somebody who's 5'8", those are consistent. That's just plus 1 inch. Plus 1 inch. Those are consistent intervals. So typically things that are measured, like height, weight, temperature, things like that, reach the interval level at a minimum. And then the ratio level, again, has all the characteristics of interval and below, but you also have what's known as a true zero. So there's a true zero, but what that also does is that the ratios are what they call meaningful. And what they mean by that is, can you say that when you double it, that's truly double? Or if you half it, is that truly half? So let me give you an example. So if you say, it says it up here, but I just didn't talk about it. So if you say 80 degrees Fahrenheit is definitely 20 degrees warmer than 60 degrees Fahrenheit, but you can't say 60 degrees is twice as hot. Okay? 60 degrees is not twice, I'll say 2 times, as hot as 30 degrees. It's 30 degrees hotter than 30 degrees, but we don't typically say it's twice as hot. That doesn't really make sense. You wouldn't say, oh, today it's 50 degrees and then it's supposed to be, or we'll go even something, say one city is at 30 degrees and another city is at 90 degrees. You wouldn't say that city is 3 times as hot. So if taking it times 2 or times 3 or cutting it in half doesn't make sense, it only reaches the interval. But if it does make sense, if 2 times, 3 times makes sense, then it reaches the ratio level. So temperature does not reach the ratio level, but height, weight, and things like that do. Another way in which temperature fails to reach ratio level is that there really is no true zero with temperature. There is absolute zero, which is kind of more of a concept than an actual zero. I'm not going to go into that because that's not my expertise, but it's kind of a concept. It's something that scientists believe can be approached but never reached. So it's not really a true zero in the sense of, you can have something that has a height of 0. One thing that I do talk about with the height, because you can't really think of a person's height as 0. Think of it more along the lines of, let's say you took a bowling ball and you measured how much it bounced when you dropped it on concrete. It would be, measurement-wise, it would bounce potentially 0 inches high. And so height can be 0, but again, not temperature. So as I promised, I have a couple visuals here that will hopefully help you see these levels of measurement a little bit easier too. You won't find these in the book. I put these together myself. And there's a couple different ways to look at it. Some people kind of like to think of it as like a pyramid where you kind of sift out different things as you go up. So, the least amount of data values reach ratio, but again, everything is at nominal. But let's look at these a little bit. So nominal is all data. This is a Venn diagram. So all data falls within the circle of nominal, because that just means you can name it. If you can order it, then it reaches the level of ordinal. If it has units, if you measure it, then that reaches interval level. And then if it has a true 0 and doubling or tripling or cutting in half makes sense, then that is the ratio level. And so everything that is ratio is also interval, is also ordinal, is also nominal. So these are like they're all subsets of each other. So when you're ratio, we usually will say that the measurement level is ratio, but that means it still meets all the criteria for interval and ordinal and nominal. And over here, it's like they build on each other. So nominal means it can be named. That's all data. Ordinal means it can be ranked. Interval usually has a unit of measure. And so the intervals between each measurement are equal. And then if you reach ratio, it has true 0, and 2 times, 3 times, or half makes sense. So hopefully one of those visuals will help you a little bit too. So let's look at some examples. So it says zip code. What level is that? Well, zip code actually only reaches the nominal level, because even though that it's numbers, this is one of those unusual ones that it's numbers, but it only reaches the nominal level, because zip codes don't really have any, the numbers don't really reflect anything. You can't even say that, you wouldn't say that, oh, I have a smaller zip code than you. You can't even say, oh, this zip code is further to the east because it's a bigger number, or further south because it's a bigger number. They really are just kind of randomly. The only thing is zip codes that are close to each other might be close to each other. So that really, zip codes only reach the nominal level. And so that's over in this chart too. So it reaches the nominal level, but it doesn't reach the ordinal level. So the highest level is nominal. Pizza size is ordinal. This is kind of like the drinks that I was talking about before. You can order it. You could say a small pizza is smaller than a medium, is smaller than a large, but they don't have any interval sizes between them. Even if you put them, as in some places talk about like how many inches diameter their pizzas are, it's usually not like a consistent. So it's not like, oh, if you go from a small to a medium to a large, you add the same number of inches. So a small might be 8-inch, a medium might be 10-inch, and then a large might be a 15-inch. So they don't necessarily have the same interval between them. So it only reaches to ordinal level. And then SAT scores are interval level because that's a measurement. So if you're talking as far as scores, it does make sense to say that a 1450 on an SAT is 200 points more than a 1250, but it doesn't really make sense to say that somebody who got a 650 or a 1300 did twice as well as somebody who got a 650. It doesn't even really mean that they got twice as many problems correct, because as you go up in numbers, it's only a few more problems correct. They do a bulk of kind of lower level, then mid-level gets a little bit less, and then as they go up and up, to get those higher scores, you just have to get a very few upper level difficult problems to raise that score up. Age ratio, or age is ratio level, because you can have an age of 0. Again, try to get away from even thinking of people. If you think of, say, cell growth, okay, so when a cell develops, it's at the age of 0. When it's a day old, it's 1 day old, 2 days old, 3 days old. But age is ratio level, because it has a true 0. You can have a 0 age as a start, and then if somebody is 15 years old, 15 days old for the cell, that's twice as, or half as old as somebody who's 30. Somebody who's 30 is twice as old as somebody who's 15. That makes sense. So we've talked about, they have ACT score here. That's the same as the SAT score. They have age. Hair color only reaches nominal because you can't order hair color. You can't even say one color is darker than the other. Somebody with red hair, could you say that red is always darker than brown or brown is always darker than red? You can't. So hair color only reaches the nominal level. It does not reach the ordinal level, and so it's only nominal. Letter grades, those you can order. So it does have a name because everything has a name. It can be ordered, but they're not equal intervals. Think about the difference between an F, which goes from 0 to 59 in most cases, and then a D, which would go from 60 to 69. And so those aren't equal intervals. You have 0 to 59 for an F, and then only 60 to 69 for a D. And so you can order it, but the intervals are not equal, so it only reaches as high as the ordinal level. We already did ACT and SAT. Height, we talked about many times. It's nominal because you can name it, you can order it. The intervals are the same, so you're measuring in inches. And then ratio, it does make sense to say that somebody's twice as tall as somebody else. So this reaches all the way up, so it's interval level, or ratio level, I'm sorry. Here the ACT did not reach the ratio level, so the highest it reaches is interval. Age we already talked about, and then temperature, we talked about it in length. So we talked about why it does not reach the ratio level, so temperature is only to the interval level. Okay, so now we're ready for section 1.3. And this section is data collection and sampling techniques. And the learning objective for this section is to identify the 4 basic sampling techniques. So we're going to start with collecting data. So sometimes when you collect data, it can be done by directly observing or by looking at existing records. Or you can conduct a survey. And surveys are pretty common. In a survey, the subjects are asked questions and their answers are collected. Can be used in many scenarios. I give the example of manufacturers use customer surveys to find out how effectively to market their products. Political surveys are used to determine people's preferred policy, politicians, how they're going to vote. There's telephone surveys. Telephone surveys are less costly than in-person surveys. And people do tend to be a little bit more candid on the telephone. But the problem is doing a telephone survey requires that the population of interest has telephones, which most folks do. But they have to have the telephones. You have to have their telephone numbers. And they also have to be willing to answer a phone call from a stranger. So you may not necessarily get a representative sample from a telephone survey because there's certain people who won't answer the phone, and then you're missing out on the opinions or views or answers from all those folks that aren't willing to answer the telephone. So the third type of typical survey would be a mailed or digital questionnaire survey. And mailed could be emailed also. So some sort of digital questionnaire, mailed questionnaire. You can get a wide area. You can contact a lot of people with a mailed or a digital questionnaire. But, and the respondents can remain anonymous. And it's also fairly cheap, much cheaper than an in-person or a telephone survey. However, the problem is that the response rates for mailed surveys or digital surveys are really low. And respondents could give responses that are they say inappropriate. I would say more inaccurate because they might not understand the question or they might fill out the survey incorrectly. For instance, you might have a scale where you say, 5, 4, 3, 2, 1, rank something. And you intend, the surveyor intends for 5 to be the best, and because it's listed 5, 4, 3, 2, 1, the person taking the survey might think 1 is the best, like first place or something like that. So you might get inaccurate answers if the survey is not written well, or if the person that responds doesn't quite understand what the question asks or what the responses are. And the fourth type of surveys that we talk about are personal interview surveys. These are the best, but they're also expensive and they're time consuming. So it's where you would go and personally interview someone, do a face-to-face interview, and the person can ask follow-up questions, but it's, as I mentioned, it's time consuming, it's expensive, and interviewers have to be carefully trained. So because you want them to always ask the question in the same way, and give the same options. So, and you don't want them to lead the responders into an answer and get biased answers. So all the different types of surveys have benefits and drawbacks. So now we're going to talk about sampling methods. How do you sample? So researchers use the samples because, again, we can't usually survey the entire population, but we want it to be representative of the population. And so you want it to be unbiased. And in order for it to be unbiased, you want to pick your subjects by chance. There's 4 techniques to do this: systematic sampling, stratified sampling, cluster sampling can be by chance, but the best by chance sampling method is random sampling. And I want to say right now that it is always the best if possible. So random sampling is always, always, always the best if possible. The problem is sometimes it's not. But if you can random sample to pick the subjects, that is the very best and will be the most representative of the population because there's no bias. Everybody has a chance of being in the sample from the population, and that's the best. So now let's talk about those 4 different methods: the random sampling, the systematic sampling, the stratified sampling, and the cluster sampling. So I think most folks are familiar with at least the term random sample. So to clarify, a random sample is a sample in which all members of the population have an equal chance of being selected. For instance, let's say you have 1,000 people in your population. Maybe it's an entire class at a high school, entire grade at a high school, and you're going to sample 100 of those people. So you might assign the numbers 1 to 1,000, and then you use a random number generator of some sort. Calculators and computers, you can find random number generators, and you have it generate 100 random numbers, and then those are the 100 people that you sample. But there's no other criteria other than you just randomly select. Rather than talk about a random number generator, you could even think of it as you put in a bucket or a bin or something, you have 100 chips, and on those chips you write 1 to 1,000. I'm sorry, not 100 chips, 1,000 chips. So you write 1 on the first chip, 2 on the second chip. Again, these are all corresponding to people in your population. You put 1,000 chips in the bucket, and then you draw out 100 of them. That would be completely random because you can't see who you're picking. There's no criteria for, oh, I need to have so many evens, or I need to have so many that are below 500. Not a part of it. You just randomly pick 100 out of the 1,000. That would be random sampling. That's the best way to get a representative sample from your population, if at all possible. Systematic sampling is fairly random, but the thing is once you start with the first item, then after that, every kth member is selected. So when we say every kth, it's like every 10th, every 5th, every 20th. So let's say when people are walking into the store, you give a survey, or you ask to survey every 10th person that walks in. Well, that means that once you start with that first person, everybody between that first person and the 10th person after them never had a chance of being selected because they were in the portion that weren't going to get picked. So it's not quite as random sampling, but it's still not horrible. And it's easier because you have this system. So remember what the words mean. There's a system. Every 10th person. And then stratified sampling. Another one for the systematic one would be, let's say you wanted to find out the breakdown of the different colors of cars in a parking lot. You don't want to look at every car in the parking lot, but you might mark down, again, every 10th car, every 5th car, every 20th car. So you start with the first car and you say, okay, that car's red. And then you're going to count 1, 2, 3 until you get to the 20th car after that. Then you're going to mark that down. Then you're 1, 2, 3 until you get the 20th car after that, mark that one down. Keeps you from having to write down every single car. And it also keeps you from, but it gets you, a wide variety from across the parking lot. Okay, so next we have stratified samples. Stratified samples, if you think about where you've heard the word stratify before. So stratify or stratus. There are, the stratosphere is the different layers of the atmosphere. Stratified rocks have layers in them. And so a stratified sample can remember by the fact that it has layers. And so in this example, you break down the categories into one category and then another category from those, and then you just keep building on that. So in this case, it says the population is broken down into 3 age groups. So I'll write that over here. So we have 18 to 30, and then we have 30 to 65, and then we have 65 and older. And then each group is further broken down for gender. So you might have, from this 18 to 30, you're going to break it down into men and women, and then men and women. And what a lot of times with stratified sampling, what they do is they'll say, I'm going to start with my bottom layer. I'm going to say I'm going to have 100, and then I'm going to try to get 50 men, 50 women. I'm going to have 100, 30 to 65. I want 50 men, 50 women. Then you might even break it down past that. You might break it down to college degree or not. Okay, degree, not degree, and so on. And so you end up with these layers. You have these, this top layer would be 18 to 30-year-old men with degrees, 18 to 30-year-old men that don't have degrees, 18 to 30-year-old women that do have degrees, 18 to 30-year-old women who don't have degrees. And you have these different layers. So the layers are age, in this case, that's the first layer. Then you have gender, and then you have degrees earned. So you have different layers to your sample, and that is called stratified because of those layers. And then last, cluster samples are obtained by dividing a population into intact groups. And then you can either select one cluster or group or a few clusters or groups. You wouldn't select them all because that would be the entire population. But so here's a good example. Example is you have all the counties, parishes, or boroughs, depending on what state you live in, what they're called. But every state has subdivisions, counties, parishes, or boroughs. You take all of those from across the entire country, and then you don't pick all of them. You randomly pick 30 of those. But you pick the entire county. So you're not picking a random person, you're picking a county. And so then when you're done, you have 30 clusters of counties from all over the United States. So you might have, 2 from California, 3 from Texas, 3 counties in North Dakota, 2 counties in North Dakota, 1 in Alaska. But you have these, they're scattered across the country, but you're picking this entire county rather than picking individuals from across the country. One that I like to use as an example would be a class. If I were to say I want to get a representative sample from Lone Star College Kingwood, and all I did was pick our class, this one class, then that would be a cluster of one class because you're an intact group. But would that be representative of the campus? It may not be, because I would venture to say that students that are in statistics, they're taking statistics, are more likely to be students that are in trying to earn some sort of healthcare degree. There's lots of things. The reason that you're taking statistics, it has to do probably with your degree plan, which means it's not completely representative of the campus. But it is a cluster, and it would be easier to sample an intact class than it would be to randomly select students from across the Kingwood campus and try to get information from them. So mostly just think of a cluster as intact groups. They are clustered together. So to wrap up section 1.3, we're going to talk about some other sampling methods, and then we're going to talk about what sampling and non-sampling errors are. These aren't really considered as kind of the main 4. We talked about the main 4 of the random sampling, the systematic sampling, the stratified, and the cluster. But there's also a couple other methods, and there's probably more beyond this, but another common one would be a convenient sample, and that's where it's just out of convenience, no randomization. The example they give, all the members, say you're at a restaurant manager asks everyone at the restaurant one evening to rate the service. Well, that's not randomized because all the members of the sample were at the restaurant at a specific time. So it's probably not representative. You might have, if it's too early in the evening, maybe you have a certain age group versus if it was later in the evening, versus the crowd that comes for breakfast versus the crowd that comes for dinner. And so that's not randomized, but it's convenient. That would almost verge on a cluster sample too. So I probably wouldn't put that on a test as a question, because that one I think could be easily confused with a cluster. But in this case, it's just a convenience because it was easy for him to ask the people that were all there in the evening. And then a volunteer self-selected sample is when the subjects literally just decide whether they want to participate or not. So you might stop people in the mall and ask them, do you want to take a survey? And that's not going to be very representative of the population, because the people who volunteer for a study, or you might send out a flyer and say, hey, if you want to participate in this study, please meet at this location at this time, or you might pay them. A lot of volunteer samples are paid. And that's going to be different than people who just wouldn't want to be bothered with that. And then lastly, we have two types of errors that can happen between the sample that you get and if it represents the population or not. A sampling error is just the difference between the results obtained from the sample and the true values of the population. And you're almost always going to have some sampling error, even if everything is done correctly. It's not going to be perfect. So if you think back to the example of the hair color at the high school, I guess that, I made the inference that because we had 10 out of 200 in the sample, that would mean 150 out of the 3,000 had red hair. That's probably not exactly accurate. So the difference between the percentage of the actual population and the percentage of the sample is called the sampling error. And it just happens. It doesn't mean anything is wrong. It's just because you took a sample and it's not going to be perfectly aligned with the population all the time. But there's also, this is a worse type of error, and that's when you have a non-sampling error. And that's when the data that you have are erroneous or biased. They give the example here that you could have a miscalibrated measuring tool. So everything is off by a pound. Or you could have data that's collected correctly but recorded incorrectly. You could have data that's collected with biased questions. Any of those are going to be what we call non-sampling errors. So the sampling error occurs just because you're using a sample. Okay, so this is just because you're using a sample rather than taking a census of the entire population. So that's going to happen because you're taking a sample. But a non-sampling error is kind of more critical because it means that there were problems with your data collection. Okay, so there were problems in the data collection for a variety of reasons. Okay, so now let's get into section 1.4. And our learning objectives here are to explain or learn the difference between observational and experimental studies, and to explain how statistics can be used and misused. So, the first thing that we'll talk about are experimental studies. So what makes a study an experimental study is mostly this idea right here. So in an experimental study, the researcher manipulates one of the variables and then tries to determine how the manipulation influences other variables. So when you think of an experimental study, think of the researcher messes with something. And you'll understand that a little bit more when we talk about the other type of study. So in an experimental study, the researcher is messing with things. He's manipulating things to see what the results are from the manipulation. So in a true experimental study, subjects can be randomly assigned a group, and then treatments should be randomly assigned. We'll talk about what a treatment is here in a minute too. So you have your subjects, you have a treatment, and then you have the researcher manipulating the treatment. Sometimes random assigned groups is not possible, and in that case they do what's called a quasi-experimental study. We'll probably won't talk about that anymore after this, but quasi means like kind of experimental study. And in this case, the treatments are still assigned randomly, but the groups are pre-existing. So if you're looking at, a group somehow that you can't divide groups just randomly because they're already kind of predetermined, that would be a quasi-experimental study. So the first thing that we're going to talk about with experimental studies is what are the independent and dependent variables. So the independent variable in an experimental study is also sometimes called the explanatory variable. So the independent variable or the explanatory variable. And it is the one that is being manipulated. And then the resultant variable is called the dependent variable or the outcome or response variable. So let me make a little table. When you're in algebra class, you probably had, you talked a lot about input and output. And oftentimes with algebra problems, your X will be your input and your Y will be your output. But there's other things we can call X and Y, and I just used it, the input and output. Okay, so you can have an input and then you would have an output. These mean the same thing. It's just what you put in, what you get out, whether that's X and Y, input, output. Output can also be called outcome. I'm going to just put that with this one. We also call them the independent variable and the dependent variable. Well, why is that? Well, that's because the X or the input are independent. You select those first, and then the Y or the output follows from that. So think what independent means for like a person. If you have two friends and one is very independent, they might say, hey, let's go out to dinner and a movie. And then the dependent friend would say, okay, sounds great. Nothing, not bad or good, just the way it is. So the independent kind of leads things, and then the dependent just follows along. So the independent is what you put in, the dependent follows from that input, from that independent. And then in statistics, we use the term explanatory. So this is the input, this is what explains what happens. And then you have your response, which is the response to what you put in. So you have your input and your response, or your explanatory and your response. These all really mean pretty much the same thing. In algebra, you also sometimes will have the domain and range, but those are actually sets, not individual values. So these all really mean the same. And in the experimental study, researchers are trying to determine how changing the independent variable, so you change this one, and you see what happens to the dependent variable. So the researchers are trying to determine how changing the independent variable affects the dependent variable and how powerful that effect is. So like how reliable does a change in the independent variable result in a change in the dependent variable. So now let's look at an example. This is a medical research example. It says, think about back to our experiment on the efficacy, which is the how good it works, of a heart attack preventative. Half the sample received the new drug, and the other half of the sample received, this says the old drug, but I think the example actually said a placebo. And then the number of heart attacks in each group was recorded. The independent variable in this study is which treatment the subject got, the new drug or the, I'm going to cross this out because I know that was placebo. Somebody didn't match up the slides very well. Received, again, this was a placebo. So the independent variable is whether they got the new drug or whether they got the placebo. And so you have two groups in the study that should have been randomly assigned to which group that they're in, and then randomly decide which group gets the placebo and which group gets the new drug. And then the dependent in this is whether or not the subject had a heart attack. So if we think about it in the table form, your independent and then your dependent, in this case, the independent was which type of medication or which drug, or the drug or the placebo, and the dependent is whether or not they had a heart attack. So the input was the medication, the output was the health results from it. In a study, you have the two groups we just mentioned. We mentioned that you had your treatment group, or we mentioned that you had the group that took the medication and the group that had the placebo. So in this example, the treatment group was the group that had the new medication. And then the control group was the group that got the placebo. And by comparing the differences between the treatment group and the control group, the researchers can determine how effective it is. So what happened with the treatment group, the ones that got the new drug? What happened with the group that only got the placebo? Was there better results from the people who got the new drug? And the treatment group is the group that receives the new drug, and then the control group, the reason they call it a control group is because it's like that group just stayed steady. They weren't affected by anything. Sometimes it might be a new drug and an old drug. In this case, it was a new drug and a placebo. But the control group is supposed to be the group that doesn't get any sort of treatment. We use the term treatment, but treatment's not always a medication. It could be something else. It could be any number of things, but it doesn't have to be related to medication. And the advantages of an experimental study is experimental studies, they have a lot of control. So in an experimental study, you have lots of control of the subjects, how they're assigned to the groups, how the groups differ. Researchers can also precisely change the variable. And, so they could, for instance, in the group, the one we just said, you could have had two different treatment groups. You could have had a treatment group that had the new drug at one level of, the number of milligrams in the tablet, and another group that had a higher number of milligrams in the tablet. And so you could have more than one treatment group and then just have your one control group. But the researcher has a lot of control over what they can do with that independent variable to see what the effects are. And so it makes it easier for them to understand how the independent variable is affecting, how this independent variable is affecting that dependent variable. So experimental studies aren't without their disadvantages, though. One of the major things is that experiments are done in an unnatural setting oftentimes. And so what happens in the lab or in the unnatural setting may not occur in the same way in real life. One example of this is called the Hawthorne effect. The reason it's called the Hawthorne effect is because it actually happened during a study at a plant called the Hawthorne plant. And they were trying to determine if changing the lighting would help improve the work productivity. And so they increased the lighting, and the workers improved productivity. But then it was determined that may have possibly been because they were being watched more. So they were thought that their supervisors were going to know whether they were working hard or not, and they were working harder because they were being observed. And so that type of thing is called the Hawthorne effect. Another problem is what's called confounding variables. And this is when you have variables that affect the output but can't be pulled away from the input. So a good example of this that's often given is you put subjects on an exercise program, or you give them some sort of a weight loss pill or something like that. But once you do that, they might be hyper-focused on their health, their weight, those types of things. And so while they're participating in this new exercise program, they might also change their diet or other healthier habits like getting more sleep or something like that. And so you cannot tell at the end of the day whether or not it was the exercise program that helped, or it was because they changed how they were eating or they slept more. And so you can't pull away, your goal is, okay, we have this exercise program and we're trying to see how that affects weight or it says improvements to their health. We'll just say weight. Okay, so exercise, how does that affect that weight? That's what we're trying to figure out. But connected to this exercise is also the diet, is also sleep. Maybe they are drinking less. Maybe they're smoking less or stop smoking. So all these things are kind of connected to the exercise, and yet they could also affect the weight. And so you don't know when the study is done if the exercise program is what caused any changes in weight, or whether it was one of these things or a combination of these things. And those are called confounding variables. I always think of it like Scooby-Doo, like, oh, you confounding kids, you messed up my plan. And that's what confounding variables do. They mess up the plan, they mess up the determination of the relationship. Another interesting thing that can happen is there can be a placebo effect. The placebo effect has been very highly studied. It's been proven that it definitely happens. And that's when you get a favorable response or improvement due to the fact that they're participating in the study. So the example that's given here is the researchers actually split these patients or these study participants into 3 groups. One group got an antidepressant, and another group got absolutely nothing, and then another group got a sugar tab. Okay, but they don't know that. Nobody knows, the groups don't know whether or not they got the antidepressant or the sugar tab. Obviously, the group that got nothing knows they got nothing. But they found that in this case, the people who took the sugar tab still reported lower depression, improvement in their depression. So why did that happen? Well, because they wanted it to work, and so it worked. That's basically what happens with that. They wanted the treatment to work, and so it did work for them. Now, would that work long term? Probably not. Not a good idea to give people, sugar tabs when they need medication. But in a research study, that can happen because the participants want to be in the treatment group that's actually getting whatever's being studied. There's actually a famous MASH episode where MASH is an old sitcom. I'm sure a lot of you know it, but if you don't, it's an old sitcom. It took place at Army Hospital in a combat zone, and they ran out of pain medication for these soldiers that had had surgeries and injuries, and they weren't going to be able to get any pain medication for them for a while, and they didn't know what to do. So they decided to give them a placebo and hope that just thinking they had gotten pain medication would help. And, the episode was that, it did help some of them. until they were able to actually get some pain medication. And so that idea that just by taking something, you feel like there's a change being made, or by doing something, a change is being made. So let's go to talking about blinding. So blinding is actually really important in research studies, and it sounds like something really fancy, but all it really means is that a blinded study is where the subjects do not know if they are in the treatment or the control group. And this study should always be blinded whenever possible. If they're not blinded, then you're going to have some of those results we were talking about even worse, because if the subjects know what treatment they're getting, that's going to affect the outcome. And so in a blinded study, the subjects do not know if they're in the treatment or the control group. Now, even better than a blinded study is what's known as a double-blinded study. And that's when neither the subjects nor the researchers know which group the subjects are in. Now, you say to yourself, well, how does that happen? Well, sometimes you have a third party do the assigning, and then you have what you're giving to the patients or the participants as a treatment. You have them look identical. So, there's a group that gets assigned to, group 1, and there's participants that get assigned to group 2. And then group 1 is from somebody that's outside the research study, gets assigned, tablet A, and group 2 gets assigned tablet B. But nobody that is actually conducting the research and gathering the data knows whether A is the actual, in this case, the actual medication, or if it's the sugar pill. So nobody, the researchers don't know whether or not A or B is the drug or the sugar pill. And then that removes bias from the researchers as well as the patients, because human beings are very apt to be biased. If the researchers know, oh, group 1 is getting the medication, then they could do things that could affect the outcomes. They could look at results a little differently. They could record results a little differently. They could speak to that group a little differently when they're gathering the data. And so being double-blinded is even better than just a blinded study where the subjects don't know. It's even better if the researchers don't know which group is getting which, whether they're the control group or they're the treatment group. So the terms that we're going to talk about here first are randomized design and blocking, and then we're going to talk about matched pair design. So when the subjects are assigned to the groups completely randomly, and the treatments are assigned randomly, which is how we were talking about those other groups, that is called a completely randomized experiment. So you have everybody that's going to be in the study, and then they are randomly divided into 2 groups, or you could have more than one treatment group, but in this case, let's just say there's a treatment and a control. They're randomly divided and placed either into the treatment or the control group. And that's considered completely randomized. There's no blocking. Now, sometimes you have something that you think is going to affect the research, and you'd like to block those subjects out, or the participants out into a block before you split those blocks. So in this case, it says, say researchers have a reason to believe men and women will react differently to a heart attack prevention drug. And so to control this confounding variable, the confounding variable is whether you're a man or a woman. So they decide to block the group. So before they split them, they separate them, men and women, and then they block them, and then they randomly assign them to the medication or the placebo, or the new and the old. And so you block them out. And so there's these 2 separate blocks before you do the randomization. Another thing that sometimes will happen, or that researchers will use when they find it necessary, is they'll do what's called a matched pair design. So in this case, you have all these participants, and the first step is, because you want the groups to kind of be the same, you can match them by their attributes. So in this case, let's say the subjects in the sample are sorted by age and then assigned to the treatment and control groups in pairs. Well, then each of the treatment and the control groups would have almost the same distribution of age. So say you have, in this case, 8 participants. You take the 2 youngest, the next 2, and you pair them up. And you put, here's your first pair, and then you randomly assign which of them goes to the treatment and which goes to the control. Then you have your next pair that's maybe the next oldest, and you randomly assign them to the treatment or the control. And you do that for each pair, who are as close to age as possible, and then you will end up with the treatment group and the control group being similar in their average ages. Or not even just in their average, but in their distribution of ages. And so it's a useful alternative to blocking if you're worried about confounding variables. So in this case, it would take out the age factor if you were worried that age was going to affect your study. And so by putting if you're worried that age would be a confounding variable, then you're able to distribute those ages rather evenly between the two groups to kind of eliminate that. And then replication is just the idea that in order to really truly validate studies, a lot of times they'll be replicated or repeated. Sometimes they're repeated by the same researchers again. Sometimes they'll be done by other researchers. But the idea is that if a study is valid, it should be able to be replicated. You should be able to do the study again and get similar or the same results. And that makes a study or makes a determination from studies a lot more trusted and strong in like the scientific world. So just really briefly, we have these general guidelines for an experimental study. You're going to formulate the purpose of the study. We're not going to be conducting any studies, but this is what a researcher would do. They would formulate the purpose of the study. Then they would identify the variables. What do they want to change in order to see how what outcome it causes? And so that's the treatment. Identify the variables or the treatment. And then once that's done, you're going to define the population and collect a sample, or what sampling method you're going to use. Then you're going to collect the data, and you're going to summarize and perform any statistical calculations, and then you're going to interpret the results. And so that's the general pattern for an experimental study, or the experimental design. So here's an example. It says that we're going to try to determine whether it's an experimental study, if it meets the criteria, what in the study are the independent variable and the dependent variable, and what could you think of as compounding variables. So in this case, it says researchers randomly assign 20 people to each of 2 different groups. Group 1 watches a motivational video about succeeding despite adversity, and Group 2 sits in a quiet room for 15 minutes. Both groups then solve a Sudoku puzzle, and the time required for them to complete it is recorded. So was this an experimental study? And I'll give you a minute to think about that. Does it meet the criteria for an experimental study? And the answer is it is, because you have a treatment group and you have a control group. The treatment group would be the ones that watch the video. The control would be, well, I'm kind of giving that away, but I guess not. The treatment group is the ones that watch the videos, and the control would be the group that just sat in the room. And then you take those and you see how does the treatment affect their time required. So you have a treatment and a control group. You have your two groups laid out, everything fits for what an experimental study is. So the independent variable is whether or not they watched the video or they just sat. That's the independent variable. So whether or not they watched the video. And then the dependent variable is the time for the puzzle. So whether or not they watched the video, and then how does that affect the time for the puzzle? And then what are some possible confounding variables? Well, you could have just general ability. So, you may have someone in one or the other group that has ability or experience with Sudoku puzzles. You could have whether or not they you could even have some people in the treatment group. Did they actually watch, or did they just kind of space off during the video? Did you, in the quiet room, was the group together? Were any of the people affecting anybody else's mood by sitting in the room together? Were they bothering each other, or were they just sitting quietly? You also have just a general mood and general desire. Like, do they want to show that they know how to do this, or do they not care? So let's look at what they had for answers. So they do say it is an experimental studies. The researchers randomly assigned the subjects to groups and then randomly gave them the treatment. The independent variable is whether or not they watched the video, and the dependent variable is the time to complete the puzzle. And then they list as confounding variables: familiarity with Sudoku solving techniques, skill at mathematics, education level. But they say that the random assignment should eliminate the effects of those. So you should get some in each of those groups as long as you randomly assign them. So we've talked about how at the beginning of this section, how there were two different types of studies, but then all we've talked about is experimental studies. So now let's kind of pick up on the other type of study. And this one, there's really not as much to talk about. In fact, we're almost done. I know that we're kind of at the 2-hour mark, and I was trying to kind of keep it under that. But the other kind of study is what's called an observational study. And so remember when we talked about at the beginning of experimental studies, I said experimental studies is where the researchers mess with things, when they manipulate things. In an observational study, that's not the case. The researcher merely observes what is happening. So examples of that would be watching the flow of traffic at an intersection, doing historical research into the relationship between indoor plumbing and public health. Like, at what point did a city get indoor plumbing throughout the city, and did that affect their cholera rates or their rates of infant death or something like that? And so those types of things are what's known as observational studies. There's no treatment, there's no control group and treatment group. You're just watching what is there. The advantages to that is they do occur in a natural setting, and the artificial setting of an experimental study can make people act differently. Also, another big advantage is that sometimes it's unethical or impossible to study some things using an experiment. For instance, you cannot ethically conduct an experiment on the effects of smoking during pregnancy. You can't say you're going to be in the group that smokes during your pregnancy and you're going to be in the group that doesn't, because that's already known to be a possible detriment to the health of the newborn. And so that wouldn't be ethical to assign people to those groups and, encourage them to smoke during pregnancy. So it would have to be something that would be collected afterwards. If researchers wanted to determine the effect of left or right-handedness, they can't randomly assign subjects to a left-handed group or a right-handed group. People are either left-handed or they're right-handed, or they're ambidextrous, but you can't change that. You can't say, oh, for the next 2 weeks, you're going to be left-handed. And so they can't randomly assign them. So in that case, again, it would be watching the observations based on the groups that have already been assigned. And so it's not an experiment because you're not randomly assigning the groups, and you don't have a treatment and a control group again. So some disadvantages of an observational studies is they don't have the researchers don't have any real control over the variables. So sometimes it's harder to definitively establish a cause and effect relationship. Also, it may require the researchers to travel to a distant location, spend a lot of time, those types of things. So it takes a lot of time on the part of the researcher usually. And then observational studies can sometimes depend on a third party and that the researcher doesn't have any control over. So let's say, again, you're looking at when was plumbing installed in a city and what did that do to the cholera rates. Well, you don't know how accurate the data was that was collected, 100 years ago, 200 or 150 years ago. So you don't know how accurate the data that you're looking at is, or maybe some of it's missing or things like that. So those are the disadvantages of an observational study. Okay, so to finish up section 1.4, we're going to talk about the uses and misuses of statistics. So basically some problems that can occur if researchers are not knowledgeable or careful. So sometimes data will be reported in what's known as a detached way. This is when the statistics are presented without a comparison, and that's deceptive. So if it says that a product has 20% less fat, what are they comparing it to? Are they comparing it to a prior product, like a prior product that they used to make? Is it a low fat versus their regular product? Is it being compared to typical? Is it being compared to another popular specific product? So, let's say it's 2 types of cereal. Are we comparing the current cereal to the most popular cereal? And so if you don't say what it's being compared to, then 20% doesn't mean anything. 20% of what? You can't calculate that. And so that's called detached statistics because it's not attached to the data or the information that you need. And those detached statistics, those are oftentimes used in advertising. A lot of these things, these misuses of statistics, are used in advertising. So implied connections are when you basically kind of insinuate that there's a connection, but you don't really have reason to believe it or any proof of it. So it might say, for instance, a breakfast cereal might say, it may help prevent heart disease, but they don't give any proof. There's no reason to believe it does. So you don't know if they're telling the truth. So they're implying it. It might, maybe, could. Whenever you hear those terms, then there is a good chance that they're using implied connections because they're not giving any supporting evidence for what they're saying. When reporting data, sometimes graphs can be misleading. They might mislabel the axes, or they can cut the axes so that it doesn't start at 0. There's several different things that you could do to make a graph misleading, to make it look better or worse than it actually is. And then faulty survey questions is when a survey question is either vague or it's biased, so you try to encourage a specific response. So an example of that might be, let's say you're asking students that go to a school that requires uniforms. You might say something like, many students don't like wearing a uniform. Do you agree? Well, you're leading them into saying yes. By saying many students don't like the uniforms, do you agree? People are more likely to say, yes, I agree, than if you asked a question like, do you like wearing a uniform to school? And then give them some sort of a scale, 1 to 5 or something like that. Or what are your thoughts on wearing a uniform to school? That leaves it more open. They can give an honest opinion without being led into an answer. And then some other things that can be misuses of statistics, suspect samples. This is when your sample may not be very random. For instance, when there's a very small sample or a volunteer sample, 3 out of 4 doctors recommend this product. Well, that's not very impressive if they only asked 4 doctors, or if they asked 4 doctors that already use the product. Another one is if, let's say, you talk to people as they're walking out of a science fiction movie, like a Star Wars movie, if they like science fiction. Well, that's kind of suspect, because the people that are walking out of a science fiction movie are going to be biased to saying, yes, they like a science fiction movie. Now, maybe some of them got drugged there by a friend, but if you're walking out of a Star Wars movie, probably more likely to say, yes, you like science fiction. And so those samples are suspect. And by the word suspect in this case, we mean questionable. So the sample that you are taking is questionable. Ambiguous averages is when a researcher is kind of cherry picking what they think is the best, will make their data look the most like they want it. If they want something to look bad or they want something to look good, they could choose between like the mean, the median, the mode, or the mid-range, and they could just call it an average, because all of those are actually considered averages. So depending on what they're presenting, they could make it look better or worse. And then changing the subject is where you, again, kind of choose how to word things so that it sounds better or worse. So if you were trying to say that the change in GDP, if your goal was to make it look like it was small, you could say 0.1%. If you wanted to say it had changed and you wanted to make it sound big, you could say it had changed by 20 billion. And so depending on how you decide to report that, in what sort of subject matter, in a percentage or in an actual dollar amount, makes it sound different depending on what you're doing. Okay, so the end of the first chapter of your statistics class is Insight. We are on section 1.5. This is a really brief section because it is on computers and calculations. And we don't use any type of special program in this class. We just use a calculator. There are very important computer programs and calculators that can do statistics. I tend to stay away from a lot of that. There's a couple different reasons. First of all, a lot of times the programs are expensive. Also, the TI-84 calculators can be expensive, and requiring everybody to have one of those makes things more difficult. Also, I've found in the past I've tutored students who are using technology-based statistics classes or are taking technology-based statistics classes, and their whole focus has been on how do I get this into the computer or into the program correctly, but they don't really understand what they're doing. So I try to focus in my class more on the meaning of things and understanding things, and then stick with the basic calculations, just using a calculator. If you understand the basis and the foundation of things in statistics, if you need to or want to learn how to use a program for that later, that's the easy part. And so I don't want to complicate things right now with computer programs and a lot of calculator work any more than we have to. I mean, we have to use calculators, but I don't want to complicate things any more than we have to, where the focus becomes the technology. And so we're just going to work on making sure you have a very, very good foundation of these concepts and these skills that you're going to learn and understand what they mean. And then that way, if you want to do anything more with those in the future, you'll be able to, because you'll have a good foundation. So some of the things that you can use, though, to do calculations for statistics, the TI-84 Plus actually has a lot of features that will do statistics. If you have a TI-84 and you want to look things up, it can do a lot of things. Microsoft Excel can actually do a lot of things, and I know most computers that are PCs will have Excel on them already. So again, if you'd like to learn how to use Excel, you can look things up, you can practice things, but we're not going to use those in class. And then another real popular one is called Minitab. So that's where we're going to end. Hopefully you should be very well prepared to do your Chapter 1 homework now in Alex. So make sure that you work on that before the due date. And I would highly recommend that you watch the videos, watch the lecture videos before doing your homework. I know it is time consuming. It does take some time. But if you watch the lecture videos, in the end, the homework will be easier and you will understand it better, and you will comprehend it better, and you'll internalize it better. Which will help you do better on the tests. So please, I encourage you to continue to watch the homework or the videos, the lecture videos before you do your homework. And just think of the lecture videos as being like going to class. If you were in a face-to-face class, then you would be hearing the same things that I'm telling you in these videos, you'd be hearing live in class. So the lecture videos replace attending class. So think of the lecture videos as your class attendance. And if you were taking a class face-to-face and you never came to class, you probably wouldn't be very successful on the homework and the exams. And that's kind of the same thing that's going to happen with the lecture videos for this class. So with that, I will let you go, and good luck on your homework, and I will see you back for Chapter 2.